Assalamualaikum warahmatullahi wabarakatuh and good day to everyone and to Dr. Muhammad Iqwan. We are from Group 8 here to present to you Bioprinting of Bone. So the bone dynamics or bone homeostasis refers to the balanced process of bone resorption and bone formation. Improper bone homeostasis leads to bone failure where medical treatment must be administered. So the tissue engineering research opened up a path for the development of bioprinting for bone, utilizing bone scaffolds, growth factors, and osteoprogenitor cells.
Now, let's talk about the clinical needs for bone grafts and substitutes. There are a few conditions that leads to bone deficits. Firstly is trauma. 16.2 million fractures are treated annually. It is usually common in the upper extremities, often required grafting for non-union fractures. Secondly is cancer. Cancer can lead to bone deficits, such as bone and joint cancer, bone metastasis, that is usually found in younger patients. Thirdly is arthritis and rheumatic disease. It affects 22.7% of adults, which is the leading cause of disability. Over 1 million joint replacement is performed yearly. Lastly is infection and decay. Osteomyelitis, which is dental caries, can lead to bone loss. It requires antibiotic therapy and also surgical reconstruction. Now, let's talk about how bioprinting addresses clinical needs. Firstly is custom implants tailored to patient needs. Bioprinting actually allows for the creation of bone implants tailored to specific dimensions, size, and requirements of specific patients, leading to a better fit and also function. Secondly is for safety and efficiency. Bioprinted bone has the potential to reduce complications associated with traditional bone grafts, such as infections and also body rejection. Thirdly is future direction. Ongoing research aims to improve the mechanical properties and vascularization of bioprinted bones, ensuring long-term durability and also functionality.
So now let's move on to the bone biology. Bone is a dynamic tissue consisting of minerals like calcium carbonate and calcium phosphate, along with some other collagen fibers, periosteum, blood vessels, and various kinds of bone cells. These cells include osteoblasts, which produce the bone matrix, osteocytes, wrapped inside this matrix, and osteoclasts, responsible for bone reabsorption. Moving on to the types of bone, we have cortical bone, which is dense and found in peripheral regions, and trabecular bone, which is porous and located internally. In the embryonic stage, the bone formation begins with the condensation of the menisci. This can lead to intramembranous ossification, forming flat bones, or endochondral ossification, forming long bones through chondrocytic stage. The periosteum covers the external bone surfaces and houses bone progenitor cells, while the bone's unique extracellular matrix contains hydroxyapatite crystals and collagen. Lastly, the bone marrow fills the inner cavities of the bones, aiding in hematopoiesis or blood cell formation. Red marrow is predominant in children's long bones and certain adult bones, while adults have more fatty marrow in others.
Wound healing procedures. So we have autograft, alloplast, and allograft. Autograft, alloplast, and allograft. Allograft involve transferring tissues from one part of the body to another in the same individual. Okay, it's considered as a gold standard for wound healing because of ideal properties such as biocompatibility, non-toxicity, non-allergenicity, and lastly, mechanical reliability because it came from the same person. So for autograft, it provides a scaffold for bone growth, growth factors for cell recruitment, and lastly, stem cell for bone formation. For non-vascular bone graft also, it happens for small defects with ideal wound bed condition, and for vascularized bone graft, a large defects or compromised wound beds. For alloplast, it's a procedure involved with a tissue from another donor from the same species, okay, but different individual. So like uh, person A need a donor from patient B, alright? So it's derived from cadaveric tissues and come in a various form such as a fresh bone, freeze-dried bone allograft, and demineralized freeze-dried bone allograft, where alloplasts act as a scaffold and retain some osteoinductive because of the cells was removed during the process. Okay, so appreciate your bones. So this is the last wound healing procedures, which is allograft. So allograft is also all alloplasts are synthetic materials used as substitute for biological tissues, such as metal, ceramic, and polymers. For metals, Titaniums and alloy are used in implants due to their stiffness and corrosion resistance. For ceramic, the porosity can facilitate tissue infusion or attachment. And lastly, polymer, which both natural and synthetic, offer reusable and biocompatible options for tissue engineering. So, take care of your bone.
Hi, I'll be talking about tissue engineering strategies. Let's start with scaffold. Materials of scaffolds are metal, ceramics, and polymers. For design considerations, we must think about porosity, which facilitates cell infiltration, mechanical properties, which supports weight without inhibiting bone remodeling, biocompatibility shouldn't provoke an adverse immune response, and bioactivity, which enhances bone formation. Second strategy is growth factor. The is that a signaling molecule for MSC differentiation into osteoblast. The key growth factors are BMP, BTHRP, and IHH. Third strategy is cell-based therapies, which enhance bone regeneration using progenitor or stem cells, such as MSC, which differentiate into osteoblast. Fourth is bioreactors, with cultured tissue engineering constructs in bioreactors before implementation. Lastly is fabrication technique, which creates scaffold with precise geometrical and properties using methods like AM, substrate technologies, and electrospinning technique.
Hi, we have now AM bone tissue engineering implements. We got the first one, 3D metal bone scaffold, which involve using additive manufacturing techniques to create a metal implement trial for bone tissue engineering. Selective lasers, centering SLS use a high power laser senior metal powder layer by layer. Now we have the second point is that the ceramic bones scaffold. Ceramic bone scaffold are typically made from the biocompatible materials like trisconium phosphor, which mimic the national bone mineral and promote bone growth. We go to the third point, which is the soil kite polymer bone scaffold, which is utilize the technical like selective laser, centering SLS, and digital light processing DLP to create a triple precise polymer structure. And we go to the fourth and last point, which is the hydro-based cell printing and spraying. And it's involve the deposition of the hydrogel containing cell and growth factor to create a scaffold for tissue engineering. Thank you.
Subtractive and other non-AM techniques. Subtractive manufacturing involves the removal of material from a solid block to create the desired shape. This technique includes milling, drilling, and also laser cutting. This technique commonly used for creating a precise and complex bone implants. Next, electrospinning. 3D printing and electrospinning are used to fabricate complex structures with improved properties. Combining 3D printing and electrospinning potentially creates a composite structures with even superior properties for biomedical applications. Electrospinning in 3D bone bioprinting produce nanofiber scaffolds that mimics the natural ECM, useful for creating scaffolds with high surface area for cell attachment. The last one is decellularized ECM. Decellularization is the process of eliminating cell and their components, especially DNA and RNA, from the extracellular matrix to yield a natural matrix with safe mechanical integrity. In bone 3D bioprinting, decellularized ECM obtains scaffolds from natural tissue by removing cellular component while preserving the ECM structure. It provides naturally occurring scaffolds that support cell attachment and growth. As you can see over here, these are the example of decellularized ECM in bone.
In conclusion, the various bioprinting techniques have been employed to create both simple and complex homogeneous and heterogeneous structures, and these techniques show promise in mimicking native tissue properties and promoting cell integration. So the challenges to address in bioprinting of bone is the need for higher temporal and spatial resolution at micro and macro scales to mimic complex structures, as well as exploring additional biomaterials and ensuring fabrication consistency. So that is all for us. Thank you.